Voltage series feedback. The closed loop configurations are four types. First one is voltage series feedback. Second one voltage shunt feedback. Third one current series feedback. Fourth one current shunt feedback. The first one is voltage series feedback. Here this is the block diagram of voltage series feedback. Here the main block is the input to the feedback network is taken from output of the operational amplifier, which is in parallel. The output of the feedback network, that is the feedback signal, is applied to operational amplifier as one of the inputs to operational amplifier. And for another input, the actual source input VIN is applied. Now this is the simple way of voltage series feedback block diagram. The first block is operational amplifier, which is having open loop gain capital A, and the second block is feedback network having the feedback ratio or gain of the feedback network is capital B. The output of the operational amplifier is applied to feedback network. Then the output of the feedback network is applied to operational amplifier, one of the inputs, and for another input, the actual source input VIN is applied. This is the actual circuit diagram of voltage series feedback network along with the operational amplifier. So here the main source input VIN is applied at non-inverting terminal. The output of the operational amplifier is applied to inverting terminal of the operational amplifier through a network having two resistors R1 and RF. Here VO is the output of the operational amplifier, VF is the feedback signal, and VIN is the source input. The voltage series feedback is also known as non-inverting voltage feedback circuit because the actual source input VIN is applied at non-inverting terminal and the operational amplifier is with the feedback connection. So that's why it is also known as non-inverting voltage feedback circuit. It is also known as closed loop non-inverting amplifier because the operational amplifier having one and only one source input that is applied at non-inverting terminal and the operational amplifier is with the feedback. That's why it is also known as closed loop non-inverting amplifier. With this type of feedback, the input signal drives the non-inverting input of this operational amplifier. A fraction of the output voltage is then fed back to the inverting input. The operational amplifier is represented by its symbol, which includes its a large signal voltage gain AD. Feedback circuit is composed of two resistors loop voltage gain or gain with the feedback, that is capital A equal to VO divided by VID. Here VO is the operational amplifier output and VID is the difference input voltage. Next, the closed loop gain or gain with the feedback, that is AF equal to VO divided by VIN. VO is the output of the operational amplifier. VIN represents source input. Next, the gain of the feedback circuit or the feedback ratio, that is capital B equal to VF divided by VO. VF represents the feedback signal and VO represents output of the operational amplifier, that is the input to feedback network. Next, the difference input voltage, that is VID equal to VIN minus VF. Now, the characteristics of voltage series feedback. The first one is negative feedback. So the voltage series feedback is positive or negative feedback. This is negative feedback. Now we will see how it is negative feedback. For the circuit, first of all, we should apply Kirchhoff's voltage law at the input. So VID equal to VIN minus VF. That is the difference input voltage VID equal to difference of the two input signals, that is V1 minus V2. Here V1 equal to VIN and V2 equal to feedback signal VF. Next, the operational amplifier amplifies the difference voltage to certain level. It depends upon the open loop gain capital A. So in this, the feedback signal VF is greater than VIN because the feedback signal VF equal to capital B into VO. Capital B represents feedback signal ratio, feedback network ratio or gain of the feedback network, and VO represents output of the operational amplifier. That is, part of the output signal is applied to operational amplifier as one of the inputs. Next, for the difference voltage VID, the corresponding output voltage VO is always out of phase by 180 degrees phase shift with respect to input voltage VIN. Hence the feedback is negative. Here VF greater than VIN, therefore the difference voltage VID will become negative. So the corresponding output voltage is negative. That is, when compared with the input signal VIN, the output signal is 180 degrees. Difference input voltage is ideally 0. Loop gain capital A or AD equal to VO divided by the difference input voltage VD or VID. So the difference voltage VID equal to VO divided by the open loop gain AD. See, generally the open loop gain is very large and ideally infinite. It means, see, for small input voltage, for small amount of difference input voltage, the operational amplifier can show large output voltage and there is a corresponding large voltage gain. So ideally the difference voltage is 0 volts. It means V1 equal to V2. That is, the voltages at non-inverting terminal and inverting terminal all are equal. So ideally 100% equal. Then only the output can show infinite open loop gain, but not practically. So in order to show the maximum voltage gain, the input difference voltage should be low as much as possible. It means both the input voltages are very close to each other. So here V1 equal to VIN and V2 equal to the feedback voltage VF, which is equal to R1 divided by R1 plus RF into V0. Here voltage divider rule is used. V1 equal to V2. So in order to get maximum open loop gain capital A and ideally infinite, and both should be equal, both the inputs should be equal, that is V1 equal to V2. Based upon that condition, VIN equal to R1 divided by R1 plus RF into VO. Finally VO equal to 1 plus R1 by RF into VIN. Next, third characteristics, input resistance with feedback. So before applying feedback and after applying feedback, what is the change within the input resistance? That is the next characteristics of voltage series feedback. Is there any change or not? Okay, we need to analyze. See, the figure shows voltage series feedback with the operation amplifier feedback circuit. Next, in this circuit, capital Ri is the input resistance without feedback, and RIF is the input resistance of the operational amplifier with feedback. The input resistance with feedback is defined as, that is RIF equal to, is the ratio of input to input voltage to input current, that is RIF equal to VIN divided by IIN, input voltage divided by input current. Actually the input voltage, which is equal to the difference input voltage VID plus the feedback voltage VF. Actually VID equal to VIN minus VF. So from that equation VIN equal to VD plus VF. So VD plus, so VF equal to B into V0. Actually the feedback ratio beta equal to B equal to VF divided by VO. From that VF equal to B into VO, which is equal to VD plus B into, see the output voltage as in the form of input difference voltage capital A into VD. So which is equal to VD into 1 plus AB, which is equal to 1 plus AB into VD as in the form of input current and input voltage. So that is IIN into RI. So therefore VIN equal to 1 plus AB into IIN into RI. Now take this side IIN to left hand side. Therefore VIN divided by IIN equal to RI into 1 plus AB, that is RIF, new resistance. That is the input resistance of the operational amplifier with the feedback, RIF, which is equal to RI into 1 plus AB. So here RI is the input resistance of the operational amplifier without feedback. RIF is the input resistance of the operational amplifier with the feedback, and AB represents the loop gain of the operational amplifier with feedback. Since AB is much larger than unity, it means RIF is much larger than RI. Therefore, the input resistance of the operational amplifier with feedback is 1 plus AB times input resistance of the operational amplifier without feedback. Next, output resistance with feedback. Now we are going to analyze output resistance of the operational amplifier